Hey everyone, and welcome back to the AI Research Roundup. I'm your host Alex, and today we're diving deep into some fascinating AI research. We'll be looking at a paper titled Sleep Time Compute, Beyond Inference Scaling at Test Time. The core idea here is pretty neat. You know how large language models can take a lot of compute power and time when you actually ask them a question? Well, this paper introduces something called sleep time compute. It basically lets the model do some thinking offline before you even ask your query. By anticipating questions and pre-computing stuff, it can significantly cut down the compute needed when you actually need the answer. They found it can reduce test time compute by about 5 times for the same accuracy on certain tasks. Okay, so Figure 1 here gives a really nice visual example of how this works. On the left side, you see the sleep time phase, and on the right is the test time phase. Normally, the raw context just sits there until you ask a question at test time. Then the LLM has to do all the heavy lifting, like you see for Q1 and Q2 in the top part. But with sleep time compute, shown in the bottom path, the LLM processes that raw context before any questions arrive, creating a richer learned context. This learned context, which already has some reasoning done, is then fed to the LLM at test time. The result, as you can see, is that the LLM needs much less compute to answer the same questions. Building on that general idea we just saw, Figure 2 gives a concrete example of how they set this up for their experiments. They took standard problems. Here it's a math problem from the GSM symbolic dataset, and basically split it. The background information, the setup, becomes the context that's available beforehand during that sleep time phase. And the actual question, like how many market indigo tennis balls, becomes the query that arrives later at test time. This split is what allows them to test the sleep time approach we discussed. Okay, so now let's look at the actual results on that GSM symbolic dataset we just discussed. Figure 3 here shows the trade-off between accuracy on the vertical axis and the average test time compute per question on the horizontal axis. You can see 2 sets of lines for different models. The key thing is that the blue lines, representing sleep time compute, consistently sit above or to the left of the gray lines, which are the standard approach. That shaded blue area basically shows the win. You get better accuracy for the same test time compute, or you need less compute to hit the same accuracy level. This holds true for both model sizes shown here. Okay, so Figure 4 basically shows us the same kind of plot as before, but this time for a different math reasoning dataset called stateful AIME. Again, we're looking at accuracy versus average test time compute. And just like we saw with the GSM symbolic data, the blue lines representing sleep time compute consistently demonstrate that you can reach similar accuracy levels using much less compute at test time compared to the standard approach shown in gray. This benefit holds up across the various models they tested here as well, like O3 Mini and Claude Sonnet. So, building on those results we just saw, Figure 5 gives us another important comparison. Instead of just looking at the standard sequential scaling, this figure compares sleep time compute against parallel test time scaling, specifically the pass at K method. We're looking again at the stateful GSM symbolic dataset, split into P1 and P2, and, well, the story is pretty consistent. The blue lines, showing sleep time compute, are generally outperforming the gray lines, which represent that parallel pass at K baseline for the same amount of test time tokens. Alright, and following on from that, Figure 6 basically shows us the same kind of comparison, sleep time compute versus that parallel pass at K method, but this time on the stateful AIME dataset. Just like we saw before with GSM symbolic, the results are pretty consistent across the different models shown here, like O3 Mini, O1, Claude, and DeepSeek R1. The blue lines, representing sleep time compute, generally dominate the gray pass at K lines, meaning you get better accuracy for the same amount of test time compute. So this really reinforces that sleep time compute holds an advantage over parallel scaling too, at least on these math reasoning tasks. Going further with this idea, Figure 8 now explores what happens when we actually increase the amount of compute used during the sleep time phase itself. We're still looking at the stateful AIME dataset here, plotting accuracy against test time compute for the O1 and O3 mini models. What's new is the different colored lines show different levels of reasoning effort applied during sleep time: low, medium, and high. And, well, you can clearly see that putting more effort into that offline sleep time processing, the darker blue lines, shifts the whole curve up and to the left, giving you even better accuracy for the same test time cost. So yeah, across all these results, it really seems like this sleep time compute approach offers a compelling alternative to just scaling up inference at test time. The key takeaway really is that by doing some smart processing offline during this sleep phase, we can significantly boost model accuracy without making the user wait longer or pay more for compute during actual use. It suggests a really interesting path forward, maybe rethinking how we deploy and optimize these large models. Well, that's all the time we have for today on the AI Research Roundup. Thanks for tuning in. I'm your host, Alex. See you next time.